Okay. Ciao a tutti, come state? Bene. Okay. Good morning. Fantastic. Well, it's a pleasure again to see all of you. Again, I know 9 a.m. is always a little bit of a fun challenge, but I hope that this morning's lecture is enough to keep us all vibrantly awake. So where we left off yesterday is we'd introduced the paradigm of generalized global symmetries, and in particular, the idea of higher form symmetries. And objects that are irrelevant to us as particle theorists, we recognize that these symmetries are everywhere in simple theories in 3+1 dimensions, and crucially, they are already present in the standard model. It will not surprise you, of course, that they're also abundantly present in theories beyond the standard model. And so now the question is, how can we actually learn new things using these symmetries in the context of the Hooft paradigm? And I guess I emphasized at the end of this lecture, when I started learning about generalized symmetries more than 3 years ago, most I talked to in the particle theory community said, when I described these objects to them, they said, this can't ever be useful to us. If it did anything useful, we would have seen something. Uh, and I think the thing that was important to realize is that, again, particle physics is not the art of exact symmetries. That just tells us things are zero. It is, especially in the Hooft paradigm, the art of approximate symmetries. That is to say, the effects that persist, the selection rules that persist, even in the presence of broken symmetry. And so indeed, I think this is abundantly true in the case of generalized global symmetries, that it is actually in the breaking of these symmetries that we begin to see things that are new and interesting for particle physics. So today we will simply be obsessed with the idea of what happens to these symmetries as they break. There are, of course, effectively speaking, three types of breaking that we can think about. We could think about spontaneous breaking of the symmetries, they're global symmetries. We could think about explicit breaking of them, just turning on terms that violate the symmetries in the way that we've already discussed for ordinary symmetries. And then, of course, we can talk about things that we've danced around a little bit, which is we talk about the breaking of symmetry by anomalies. And anomalies actually are the place where the generalized global symmetry structure has its richest form, because they actually allow us to mix higher form symmetries and ordinary symmetries of different degrees, and that's really the place where it can start to enter into local particle physics. All right, so our plan today will be to start with spontaneous symmetry breaking, then explicit symmetry breaking, and then anomalous symmetry breaking, depending on how I manage my pacing and making sure we have lots of time for coffee before Jesse's lectures. We may finish our discussion of anomalies and their effects at the beginning of next lecture. Okay, so let's just talk about this breaking of higher form symmetries. And to motivate, again, I'm not going to give you any proofs, but I will give you some statements and some motivations for them. To motivate what spontaneous breaking of higher form symmetries should look like, we can just think about one thing that we might mean in the spontaneous breaking of an ordinary zero form symmetry, which is that, if we have some charged operator under that ordinary zero form symmetry, and we look, for example, at the correlation function of insertions of the charged operator at different points, and then we can study this as we take these operators to large separation. One way to say that we have a spontaneously broken symmetry is that the result of this at large separation factorizes into non-vanishing expectation values of the charged operator at the points at which I've inserted it. Another way to say that, right, is when the symmetry is spontaneously broken, this quantity doesn't depend on the interval between the operators, it only depends on the endpoints, okay? If this is non-zero. All right, and then of course, if this is true, lots of interesting things follow. We have Goldstone's theorem that tells us that we get Goldstone bosons for continuous symmetries, and so on and so forth. So the analogy that this gives us to think about what spontaneous breaking of higher form symmetries should look like is we know we have charged operators. So in the case of a p-form symmetry, we know now the charged operators, there's some extended objects, so I'll write W to find the Wilson loops, for example, in the case of a one-form symmetry. They're all labeled by some charges Q, and they're defined on some surfaces, which we now know are p-dimensional for the charged objects for a p-form symmetry. And in general, given an extended object, this can compute expectation value. And you'll find, of course, because it's an extended object, right? So typically, especially when we do semi-classics in field theory, where we can actually calculate quantities associated with semi-classical objects, extended objects, we find that these things are exponentials. And in general, it will be the exponential of some quantity, which can depend in some way, so I'll just call it f, which can depend in some way, of course, on the surface on which the operator is defined. And now we have basically two options. If we take the volume of whatever the surface is to infinity, right? That's like taking the separation to infinity. We can ask questions about the ratio of this exponential factor relative to the volume. And there's two possibilities, right? Either the answer is finite or it's infinite. So sort of like Jesse yesterday, you turn on the LHC, either the universe is destroyed or it's not. It's either finite or it's infinite. And in analogy with our zero form criteria for zero form symmetry breaking, where the expectation value depended only on the points on which the operators are defined, if this quantity, right, is scales like some multiple of the volume, okay, so that the ratio is finite as we take the volume to infinity, then that is the criterion for spontaneous symmetry breaking in this case. If it instead is infinite, so it, for example, scales as whatever the volume encloses, then the symmetry is not spontaneously broken. Now, there's some subtlety in this because normally when you compute these quantities, they have divergences, and so there's always a freedom of counterterms, but this is a generically valid criteria for deciding if one of these symmetries is spontaneously broken. And just to make it more concrete, let's bring it back to one of our examples in 3+1 dimension, which is a calculation you may have already done. The calculation, I believe, it's in Mark Srednicki's QFT textbook, and it's in Petrov and Schroeder. So depending on how you learn quantum field theory, you may have already done this calculation. But one thing that you learn when you're trying to see how we get potentials in quantum field theory is, right, one way you can do it is the naive way is you compute some scattering amplitude, and then you take you Fourier transform it, right, and you consider it at zero momenta, and you extract a potential, and then you learn that's not gauge invariant, and then your QFT instructor tells you, well, you should do something else. You should compute the expectation value of a Wilson loop, right, corresponding to the insertion of two heavy charged particles at some separation, and that expectation value is a gauge invariant way of extracting the potential. And so you find, for example, if you do this calculation just for Maxwell theory in 3+1 dimensions, at weak coupling, we say, of course, that's in the Coulomb phase. The answer that you get for the expectation value of a Wilson loop goes like e to the minus gauge coupling squared times the perimeter, which when you do that calculation, right, you're computing a Wilson loop of this form, which has some perimeter p. Okay, and so indeed you find the expectation value only depends on the surface on which the Wilson line is itself defined. That's a contrast to, for example, if you do this calculation for the Wilson loop of, say, Yang-Mills theory at strong coupling, when famously the strong coupling expansion of this calculation gives you something that scales like the area enclosed. Okay, that's the alternative, and we know that's a diagnostic for confinement in the gauge theory. Now, just to be pedantic, because sometimes people are uncareful about this, actually when you do this calculation, you find that there is freedom to shift this quantity by counter terms. So whether you say it goes like the perimeter or something else is actually sensitive to your choice of regularization. But the important thing here is really what we mean is it doesn't go like the area enclosed. Okay, so that's maybe a more precise statement about the expectation value of the Wilson loop. But what this means is that the one-form symmetry, the electric one-form symmetry, of Maxwell electromagnetism in 3+1 dimensions is spontaneously broken in the Coulomb phase at weak coupling. In fact, you can do the same calculation for a Hooft loop, and if you do the same calculation for Hooft loop, you find the same behavior. So this is also the statement that the magnetic one-form symmetry of Maxwell electromagnetism is spontaneously broken in the Coulomb phase. And so actually both of these are spontaneously broken global symmetries. Now, it won't surprise you that these are just global symmetries. So there is a generalization of Goldstone's theorem that applies to spontaneously broken higher form symmetries. And it's just a statement. So I'll put it in scare quotes because in an axiomatic sense, it has some slightly different properties from the ordinary zero form Goldstone's theorem. And it's just a statement that spontaneously broken p-form symmetries have a p-form Goldstone boson. So in the case of a spontaneously broken one-form symmetry, like the electric and magnetic one-form symmetries of Maxwell theory, what would that Goldstone boson be? It has to be a one-form. Do we have a one-form boson in the theory? What is the only ingredient in Maxwell electromagnetism? The photon, right? We have a one-form boson in the theory, which is the photon. Is that massive or massless? It's massless, right? So there is a way in Maxwell theory of understanding the masslessness of the photon as following not from some protection, right? The mismatch between counting of degrees of freedom, that a massless vector has two physical polarizations and a massive one has three. So unless I give you extra degrees of freedom, a massless boson stays massless. That was a very non-symmetry based way of understanding the protection of the mass of the photon. This is now, in the spirit of generalizing the Hooft paradigm, this is now a very symmetry-based way of understanding the masslessness of the photon. The Goldstone boson of the spontaneous breaking of these one-form symmetries, and indeed, it's sort of doubly protected, right? It is a Goldstone of the breaking of both the one-form symmetry, the electric one-form symmetry, and the magnetic one-form symmetry. Now, you can ask a question. What happens if I explicitly break the symmetry? Does that gap the photon? And we'll start to come to that in a minute when we begin to systematize what we mean by explicit breaking. There's one other thing that's worth commenting on, which is, this is something, again, that as particle physicists we don't think about very much because we typically live in 3+1 dimensions or higher. But condensed matter physicists, of course, they would call it the Mermin-Wagner theorem. We would call it the Coleman-Mermin-Wagner theorem. Depends on who your heroes are. But that just tells you, right? So the Coleman, Mermin, Wagner theorem, this says there's no spontaneously broken zero form symmetry in D less than or equal to 2 dimensions. And the way that you show that is you say, well, let's imagine there was a spontaneously broken symmetry, so it should have some Goldstone bosons. And now you can simply look at the 2-point correlator of those Goldstones, and what you find is in 2 dimensions and lower, there are pathological divergences at large separation, and so that means in some sense these things become ill-defined, and that's what forbids us from actually having the Goldstones. Okay? Whereas these 2-point correlators are well-defined once we're in 3 dimensions and higher. So, of course, there's a p-form version of the Coleman-Mermin-Wagner theorem, which says there's no spontaneously broken p-form symmetry in D minus p is less than or equal to 2. Okay. So now we can ask in 4 dimensions, right, what are the spontaneously broken higher form symmetries we can have? So we now put 4 here, right? And so that tells us that we can spontaneously break 0-form symmetries and 1-form symmetries. And we've seen now the thing that we get at 3+1 dimensions from spontaneously breaking the 1-form symmetry. Okay. So, you might have gotten very excited and said like, wow, gosh, maybe, although we already had another way of saying why the photon was massless, this is a very nice symmetry-based way of doing it. It brings it into the paradigm. But maybe we also discover other things are massless that maybe we hadn't known, but we don't, right? Because when we stop at 1-form symmetries, which we already had this argument based on the mismatch of degree of freedom counting. And there was actually an exercise that, Riccardo Ortazzi provoked me to do, which is then you could go to higher dimensions. Of course, as you increase the space-time dimension, the degree of the objects that can be Goldstone bosons increases as well. But it turns out there's precise agreement between the things that can be understood as being massless because of this higher form Goldstone's theorem and the things that have a mismatch in degrees of freedom between the massless and the massive version. So you don't discover a new protected field through this argument, but you do allow yourself to promote the protection of the mass to a symmetry principle. Okay. That's all I want to say about spontaneous breaking. There's, of course, a lot more that we could do. But I also want to turn to explicit breaking before we then start to confront the effects of anomalies. Does anyone have any questions for me before I go on to explicit breaking? Okay. So when it comes to explicit breaking, again, I just want to be very concrete because I think that helps us to orient ourselves in the space. And so let's keep on thinking about just Maxwell theory in 3+1 dimensions. We already noted, right, it has an electric and magnetic one-form symmetry. It's spontaneously broken in the Coulomb phase. And now we can ask also what it would mean for it to be explicitly broken, right? So to remind ourselves, if we have a pure U1 theory, we said that we had an electric one-form symmetry, which was a 2-index antisymmetric tensor current corresponding to one-form symmetry, and that was just given by the field strength. Remember, and we said conservation followed just from the equations of motion in the absence of charged matter, and so the right-hand side was 0. Now, so then I said, okay, it was important that we didn't have charged matter, because if we did have charged matter, what we would find is actually the right-hand side would be proportional to some matter current, right? And this would no longer be a conserved quantity. So that's just one way to see, that the symmetry is indeed explicitly broken if we have charged degrees of freedom. There are other ways to make the same statement, which maybe, depending on how you think about it, give you more or less intuition. A very intuitive way of saying it is, we understood that these symmetry defect operators were topological because as we wiggled them, as long as we didn't cross the insertion of a charged operator, they always, the value of the charge that they counted didn't change. But now you could imagine if you're at energies where, let's imagine from the perspective of an effective field theory, you have some massive charged particles. Above the scale of the mass, now you can efficiently pair produce charged particles and their antiparticles. And although when you pair produce those, globally, the charge in the universe is still conserved because you produce compensating charges. Locally, maybe you've made a positive charge and a negative charge. And now if you were asking questions about symmetry defect operators, not that enclose the whole system, but maybe symmetry defect operators that run between the two charges, then you would see you've had some non-conservation of your symmetry, and so the symmetry is broken. Another way to put it is we've said the charged objects with respect to this I-form symmetry are the Wilson lines, right? So in a theory without dynamical charged matter, those are infinite line objects that extend through the theory. And a consequence of that is that we are always guaranteed, if we have a symmetry defect operator, there's a notion that if we pull it past the Wilson line, it will always link it and therefore affect the symmetry transformation, right? So this is, again, this picture where if this is the Wilson line and this is the symmetry defect operator, the surface on which the symmetry defect operator is defined, in this three-dimensional picture, we always link the two as we pull the symmetry defect operator past the location of the charged object. But if we have dynamical charged matter in the theory, that's just a statement that Wilson lines can end on a charged particle. Indeed, if you actually want to define a truly gauge invariant collection of operators in a gauge theory, you, morally speaking, should attach Wilson lines to all of your charged particles. And so now, if I have dynamical matter, I can end the Wilson line. And now, of course, I can unlink the symmetry defect operator from the Wilson line without having them cross, right? I would just, imagine this is like stepping out of a hula hoop, right? I could just rotate it down this way around the insertion of the charged object and then push it off to wherever I wanted to without intersecting the Wilson line. So once there's no longer a well-defined linking between the symmetry defect operator and the Wilson line, then there's no longer a well-defined action of the symmetry, and the symmetry is again explicitly broken. Yeah. And in a massless theory, there is never a one-form symmetry, right? There is no scale. Good. So I've been using some EFT intuition here, which is that, and this is actually important because this will come up again and again in all of our further examples. If you imagine you had a UV theory with, say, a photon and some charged fermions, and then there was a scale at which the fermions acquire a mass, and in the IR, you just have pure Maxwell theory, okay? Indeed, up here, there's the fermions are dynamical, they're fluctuating degrees of freedom, and the symmetry is simply explicitly broken. It's entirely gone. But once we go below the mass scale of the fermions, and these pair production processes now become inefficient, or they're no longer dynamical objects in the theory, now this theory has an emergent electric one-form symmetry. But if I take the mass scale to 0, right, then there is never a one-form symmetry. Okay. So in this situation, if we pass between QED and Maxwell theory, what we have in mind is in the sense of effective field theory, where the charged particles are gapped, there's simply no higher form symmetry above the scale, but there's an emergent one below the scale. And this is true again in particle physics for many of the higher form symmetries that we're interested in. Some of them are exact at all scales in the theory that we care about. For example, this is true of the magnetic one-form symmetry of hypercharge in the standard model. That's true into the UV until we encounter some other physics. But for example, if we also looked at the standard model, and we know also there's this electric discrete Z6 one-form symmetry in the UV. But if we actually go down through the mass scales of the standard model below the mass of the electron, we get a complete emergent electric one-form symmetry once we've integrated out all of the charged particles. So many of the symmetries we care about are emergent. And the idea that these symmetries are emergent and there's physics associated with their scale of emergence is extremely important. And this will really play a very important role when we talk about anomalies. Okay. So that's kind of one, in this case, that's what we mean by explicit breaking of the symmetry. In the case of periodic scalar, which we said had a two-form winding symmetry, again, the charged objects were the world sheets of axion strings. But if we reach a scale where the strings themselves become dynamical, and then, for example, I could produce a string and an anti-string, that allows me to cut the world sheet, right, of an axion string. And that's an analogy with ending the Wilson line here, that would now break the two-form symmetry. So the general, the thing to keep in mind is, in the examples that we usually encounter in particle physics, if we have something that's a gauge symmetry, right, it typically has some higher form global symmetry associated to it. What is that symmetry corresponding to? It's corresponding to conservation of some sort of charge, right? So in the electric one-form symmetry, it's counting electric flux lines. In the case of the axion, the winding symmetry, it's counting the winding number associated with strings. That's where the global symmetry is coming from. That's the conserved object. And as soon as the things that are charged under the gauge symmetry become dynamical, then they break that conserved global symmetry. Okay. So just this is a distinction sometimes people get confused about, right? We said the one-form symmetry here, the objects charged under the one-form symmetry are the Wilson lines. The objects that break the symmetry are the things charged under the gauge symmetry that gave us the one-form symmetry. Okay. So what are the consequences of this breaking? Let's imagine we're in a situation where in the UV above the mass scale of some charged particles, we have no electric one-form symmetry. And then it seems clear that as we go to the infrared, there's at least an emergent electric one-form symmetry. And if this were a zero-form global symmetry, an ordinary global symmetry, we would expect that even if the symmetry is emergent in the IR, it will have various effects that violate it. For example, irrelevant operators, local operators, so they are suppressed by some powers of the scale of the fermion masses. But nonetheless, there should be some irrelevant operators that violate the symmetry. And we know if this was an ordinary zero-form global symmetry, and we had maybe it was spontaneously broken in the infrared, and so maybe we had an ordinary zero-form Goldstone boson. If we explicitly broke it in the UV, we would gap the Goldstone. This is what we saw in the chiral Lagrangian, right? We spontaneously broke the chiral symmetries with QCD. The pions were the Goldstones, but because we explicitly broke it in the UV with quark masses, that gave masses to the pions, right? We gapped them. Okay. So now we can ask the same question here. If I have a one-form symmetry that's emergent in the infrared, and I've broken it, but I've broken it in the UV, what are the consequences of that UV breaking for the infrared physics? And the first thing that you might think is, well, it's just as bad for the one-form symmetry as it was for the zero-form symmetry. So what do I mean by that? Well, we can go ahead as effective field theorists and do this matching calculation. So we know if we have just a normalizable QED in the UV, and we integrate out some fermions, we get the Euler-Heisenberg Lagrangian in infrared, right? So what that corresponds to, we do the matching calculation, and we say, for example, if I integrated out a box of heavy fermions and attached gauge bosons to it, this is some contribution to the 4-point function of gauge bosons in the UV theory. That has to be matched in the EFT by a contact term. And since the theory is gauge invariant, the only thing that this can be is an operator of the form field strength to the fourth, right? So this is the leading term in what we call the Euler-Heisenberg Lagrangian. And so the Euler-Heisenberg Lagrangian, the EFT at low energies, now we have the ordinary kinetic term for the gauge bosons, but now we have an infinite tower of operators, all of which are functions of the field strength, right? That's the only gauge invariant object we can write down that correct the marginal part of the theory. And so now you might be concerned. You would say, well, look, how do we get the conservation statement of the electric one-form symmetry originally? Well, we just took the equation of motion, right? And there was nothing on the right-hand side, and so we were done. Now, naively, if I take the equations of motion here from the leading piece, right? Now I get d mu, f mu nu. Now it picks up something on the right-hand side, right? It's proportional to whatever this Wilson coefficient is. Crucially, because it's coming from things that only depend on space-time derivatives of the gauge field. In our normal computation of the equations of motion, it picks up a space-time derivative. And then that acts on f mu nu, f squared, and then you get a higher tower. Okay, so there's now a term on the right-hand side of the equation of motion. Is this one-form symmetry in the EFT broken? Again, 50-50. Universe ends or it doesn't. Is the electric one-form symmetry broken in the EFT? Someone said yes. No superpositions. We're all large with respect to h bar. Sorry. No, why not? Sorry. They're both sides. The symmetry properties of both sides are perfectly in agreement. So there's nothing complicates or anything. Well, it's just going to define an improved current, right? So crucially, because everything on the right-hand side, all of these operators still were also functions of derivatives of the gauge field, still gauge invariant. In the equations of motion, they always have a space-time derivative of something, right? And so now let me just define an improved current. Let me call it J prime mu nu, right? And this now goes like F mu nu minus whatever this Wilson coefficient is, F mu nu F squared, and I can improve it with all of the other terms as well, which all will have the same form when they enter the equations of motion. And this object is clearly conserved, right? So it shifts slightly what I mean by the definition of the current, but there's still a conserved object. Now, I wouldn't have been able to do this if I had charged matter in the EFT, because then there would be terms on the right-hand side of the equation of motion, which just come from the variation of the gauge field with no derivatives, right? And those would not be the form of a space-time derivative hitting something. So I could not pull them over and have them vanish in the improved current. Okay. So as long as the only things I have are functions of the field strength, I can always define an improved current. So in a different sense, this symmetry, in terms of the local operators, it becomes exact the moment we integrate out the fermions. That's surprising, right? That's very different from what we normally encounter with ordinary zero-form symmetries that were explicitly broken. Now, sometimes people go around and they make an imprecise statement. They say, yeah, actually, as soon as the symmetry emerges immediately below the scale of charged particles, it's an exact symmetry. Not true, right? What this is really showing us is we know, the things that are charged under the one-form symmetry, under the global symmetry itself, those are extended objects, okay? And so there's no local operator that is charged under the global symmetry. And so it kind of makes sense that even if I dress the EFT with lots of local operators, because they're not charged under the symmetry, they're not going to violate it. Okay, so in order to see the effects of symmetry breaking, you have to be a little bit more careful, and then you have to keep track of the extended objects in the theory, and you have to ask what they do. Now, in the case of the photon as a goldstone of the spontaneous breaking of its electric and magnetic one-form symmetries, it's doubly protected. So even though the electric one-form symmetry is explicitly broken in the UV, it's actually always still protected by the magnetic one-form symmetry, and it really is exactly massless. More generally, it can be the case, and we'll talk about some examples later if they interest you, and you should certainly ask me about them at lunch. I can have a symmetry which is, again, emergent in the infrared, and the only things that can actually break it are extended objects. And because extended objects, again, when they contribute to observables in the QFT, at least semi-classically, they come with e to the minus action suppression. And so the effects of explicit symmetry breaking in the infrared are exponentially small. So it can be that I see effects, if I have an emergent symmetry in the infrared, it isn't necessarily exact. But if it's broken in the infrared, it's typically broken by exponentially small amounts. And that again is in contrast to an ordinary zero form symmetry, where if it's broken in the UV, even by what become effectively irrelevant operators in the IR, it's broken in a power law way. So these global symmetries have a much higher quality than ordinary zero form symmetries. And that's very interesting, right? We're interested in particle physicists. We might see broken symmetries, but if symmetries are broken by surprisingly small amounts, it's hard to understand that for zero form symmetries, but it's very natural for these higher form symmetries. Okay. That's all I wanted to say about explicit breaking for now. I'm happy to talk more about that offline. Next, I want to pivot to begin to explore anomalies, which is sort of the third form of breaking. Maybe before I turn to anomalies, does anyone have any questions about our discussion of explicit breaking? I'm going to do my annoying thing again and suggest that someone ask me a question before we pivot to anomalies. Again, it could be what's my pet's name, whatever. Yeah. Good. It's at all orders. And it's just the statement that all of the operators that can appear here can only be functions of the field strength. And because that means they're only functions of field in the Noether procedure, right, they always come with these crucial derivatives, which allow us to define the improvement. So it's at all orders. Mm-hmm. Yeah. Indeed. And so I just want to emphasize, right, if I had, so, this depends on derivatives of a mu, right? And so in the variation, I'll pick up derivative of something. What's the place where I don't have a derivative of gauge field? It's in a matter covariant derivative, right? Where then I have like a mu, if it's charged, now I have a mu, psi bar, gamma mu psi. And of course, then when I do the Noether procedure, now I just get rid of this and I have no space-time derivative. And so indeed, this cannot be included in an improved current. So that's why the charged matter, once it's dynamically present in the theory, always violates the symmetry. You can ask more complicated questions like, well, what if it's just a dipole coupling? It turns out when it's a dipole coupling, that's still F mu nu, so it's still okay. Yeah. It has to be really genuine charged matter, minimally charged matter. Yeah. Okay, good, great question. All right, so let's turn now to anomalies. And although there's a very interesting and rich notion of the anomalies of the higher form symmetries themselves. For our purposes, for figuring out how anomalies are relevant in the generalized symmetries for particle physics, what we're actually going to do is study anomalies of the zero form symmetries. And then we're going to see that effectively, if I have a theory where I have some higher form symmetries and I have some zero form symmetries, when there are anomalies of the zero form symmetries, they actually lead to a mixing between the zero form symmetry and the higher form symmetry. So that's the sense in which we're going to study anomalies. It's not that the higher form symmetries themselves will always be directly anomalous. Sometimes they will be, but we'll pass those examples quickly. The examples that we'll really focus on will be situations where we have some ordinary symmetries and we have some higher form symmetries, and an anomaly in the ordinary symmetry actually leads to an interesting mixing. And that's now what brings the consequences of these higher form symmetries to bear on particle physics problems. Okay, so that doesn't require us to understand complicated things about anomalies of the higher form symmetries. We can just remind ourselves of properties of anomalies of zero form symmetries. So if you wanted to classify, let's just think about anomalies in 3+1 dimensions, right? Again, the diagrammatic way of understanding it, of course, the pathological way of understanding it is there's some non-trivial variation of a fermion measure, violates the symmetry of the quantum action. But if we just wanted to classify anomalies diagrammatically, we would say, look, anomalies arise because we have some chiral fermions, which give us triangle diagrams. And then, morally speaking, there are three classes of anomalies that we can be interested in. So one of them is just a gauge anomaly, right? If we have a zero form gauge symmetry, it can be that the chiral fermions, we get a non-zero contribution to a configuration where we have gauge currents inserted at all of the vertices. So this, of course, is just what we call a gauge anomaly. this is a pathology of the theory, right? So if we have a gauge anomaly, there's an overcounting of degrees of freedom in the path integral, and this theory is sick. You know, of course, as effective field theorists, we know it's not that you can never talk about an anomalous gauge theory. You just have to talk about it as an effective field theory with a cutoff. So don't let anyone tell you that you can't have a gauge anomaly. But if you have a gauge anomaly, your theory is necessarily not UV complete. So we're not going to worry about these cases here. Then there's two other possibilities. One possibility, as we've already encountered, is we have a triangle diagram where there's an insertion of a global symmetry current, a zero-form symmetry current, and the insertion of two gauge currents. And this is what I'll call an ABJ anomaly for Adler, Bell, and Jakif. And this has a consequence, right, which is whatever that zero-form global symmetry was, in the absence of this anomaly, it would have a conserved current. And now, as we've seen, instead, it picks up some anomaly coefficient, which depends on the matter that runs in the loop. And then this is proportional to FF dual, so some density from the gauge bosons on the right-hand side. Okay. And as we saw, right, this is a thing that spoils one of the would-be goldstones in the chiral Lagrangian and tells us that the neutral pion decays to 2 photons. The third example is actually the one that we will be mostly interested in today, and there's sort of actually two cases. One of them is that you could just imagine I have global symmetry currents inserted on all of the vertices, okay? The other possibility is I could have a gauge current inserted in one vertex and global symmetry currents inserted on the other two. This is called a Hooft anomaly. So, this is the Hooft paradigm. So Hooft is living rent-free in our heads this whole lecture series. And it's still the case, right? Whatever these global symmetry currents are, they're still good symmetries, right? There's no physical effect. You look, even if, so here, obviously, there's no gauge boson degrees of freedom attached, so there's nothing to appear on the right-hand side. Here, I'm attaching a gauge boson. I needed two vertices actually to make a gauge and Lorentz invariant density on the right-hand side, and I only have one gauge insertion, so there's no local operator, okay, corresponding to it. Good. So the order in which I want to do things today, we're going to focus first on Hooft anomalies, and then we'll turn to ABJ anomalies. ABJ anomalies we'll probably mostly get to next lecture. But let's start now with these Hooft anomalies. And the ones that will mostly be interested will be in the second class, where we have the insertion of one gauge current. But to start with, let's just remind ourselves of how this works, because this was the canonical example that Hooft gave us that motivated the idea of Hooft anomalies decades ago. How many people have encountered Hooft anomalies in their life in particle physics? Okay, just a few of you. Good. So let's all go through together what the idea was, why we call them Hooft anomalies, and what they did for us during the era in which we understood QCD. Okay. So in order to understand the consequences of this anomaly, we're going to do, now you're going to see why I made us suffer through introducing background gauge fields and coupling them to our conserved current in the first lecture, right? That method was overkill for sort of proving the validity of spurion analysis. But now you're accustomed to that idea, and now we can actually put it to work. So if we have one of these diagrams, again, it does nothing in the ordinary theory, but of course, it's an obstruction to gauging the global symmetry, right? If I tried to gauge the global symmetry by attaching dynamical gauge bosons to these vertices, I would actually have a gauge anomaly, and the theory would be pathological. So we're not going to do that. We're not going to turn on real gauge bosons. But we can say, well, what if we turn on background gauge bosons, right? And we coupled them to these symmetry currents. Then we would now have an anomaly for the background gauge fields. And so a consequence of that would be, we turn on the background gauge fields. That means now, of course, the path integral becomes a function of the background gauge fields, right? We're not integrating over them in the path integral. And equivalently, the generator of correlation functions that we use to do all of our heavy lifting becomes a function of the background gauge field. Now, in the first lecture, we said, now we imagine doing a background gauge transformation. If there's no anomaly, right, the statement was the variation with respect to the background gauge transformation vanished. And we use that to good effect. But now, if there is a Hooft anomaly, right, now the variation with respect to the background gauge transformation will generate an anomaly that is a function of the background gauge fields. And so now there will be a term on the right-hand side, some anomaly coefficient, which is a functional of the background gauge fields. Okay, but it's something that we can calculate, right? Because we can calculate these triangle diagrams, which are one loop exact in 3+1 dimension. All right, so we can actually keep track. This now allows us to, once we turn on the background gauge fields, that activates the Hooft anomaly. And now we can actually keep track of this as a function of scale, and we can use it to learn things about the theory that would not otherwise have been obvious. So I want to tell you actually how Hooft used it, okay? This is why we call it the Hooft anomaly. And Hooft's logic, this logic of we're turning on background gauge fields coupled to the symmetry currents and looking at variation of the path integral with respect to the background gauge transformation, this is a modern way of framing it. Hooft actually had a much more sort of physical way of saying it, which is, Hooft's philosophy was, look, you can't tell the difference between a very good global, an exact global symmetry and a symmetry that I've gauged with a very tiny gauge coupling, right? You can't tell, there's no observable, nothing you can measure that can tell you the difference between those two things. So how do you know when you have a global symmetry, it wasn't actually a symmetry that was very weakly gauged? And then, the consequences in both cases should be the same if you can't otherwise tell the difference. So that was his idea. So why is that an interesting thing to do? Well, let's think about it again in the language of effective field theory as a function of scale. Imagine in the UV, right, we have a theory with a Hooft anomaly, and we actually have coupled gauge bosons to it with a very small gauge coupling. Okay, so there would be some anomaly coefficient. So there's some ordinary fields in our theory, okay, some fermions, and that means that if we just coupled gauge bosons to the global symmetry current, we would have some anomaly. But that would render the theory inconsistent if this is really a gauged symmetry. So to actually make the theory consistent in this thought experiment where we've coupled gauge bosons to the current, Hooft said you also have to add some spectator fields who contribute to, they're only charged under this weakly coupled gauge field. They don't interact with anything else. You can't see them. Their only role is to compensate the anomaly from the actual degrees of freedom that you know about. Okay? So he said, great. So if, in other words, if I have a theory where in the UV, there's some, looks like a global symmetry, and some fermions give me an anomaly of the global symmetry, that should be equivalent to a theory where I've gauged the global symmetry with a very small coupling. And to make sure I haven't introduced a pathology, I also have some spectator fields who cancel the gauge anomaly. Okay, and that will be morally equivalent to your original theory. Now, what's the utility of this? Well, then Hooft said, well, now imagine, so we were interested in the anomaly of some global symmetry, but let's imagine also maybe these fermions are charged under some gauge group that becomes strongly coupled and undergoes confinement, right? So there's some interesting transition in the theory at some lower scale. And then we end up in the infrared, and we don't actually know what the degrees of freedom are, how they match to the original degrees of freedom in our theory. So this would be like in QCD, although the way that we understood QCD was from the bottom up, right? We knew about pions and baryons first, and then we saw that they came apart into quarks. Imagine you just knew about the quarks, and for whatever reason you couldn't access long distances and see the pions and the baryons. You would have a very hard time guessing, right, what the objects are in the infrared that come from strong coupling acting on these fields. But the strong coupling physics only acts on the genuine dynamical fields in the theory. These spectators, these only couple to that very weakly gauged global symmetry, so nothing happens to them as we go to the infrared. So they're still down here. They're still contributing that anomaly coefficient, okay? And then the logic was, well, something like a phase transition can't, like, if a theory was consistent in the UV, it can't render it inconsistent in the IR. So whatever the actual composite degrees of freedom are in the theory, whatever they are, they have to arrange themselves in such a way as to cancel the anomalies from the spectators, okay? Or put differently, if we just ignored the spectators because they're just along from the ride, it's a statement that if I have a Hooft anomaly in my dynamical degrees of freedom in the UV, it has to be matched by the degrees of freedom in the IR, whatever they are. Okay, so this is anomaly matching. Now, Hooft used it for QCD, right? We saw in the case of QCD, we had a global symmetry that was this SU2 left cross SU2 right. The things that were charged under it were the fermions, the up and the down quark. And indeed, these have cubic Hooft anomalies. So there's an SU3, an SU2 left cubed anomaly, an SU2 right cubed Hooft anomaly. And so now you can carry out the exercise. You can say, okay, whatever the degrees of freedom are in the infrared, they have to match those anomalies. And you have two possibilities, right? One possibility is you make bound states. They rearrange themselves into fermions. They're not the same fermions in the UV theory. They're composite states, but they're still fermions. Those fermions could reproduce the anomaly coefficient. If they can't reproduce the anomaly coefficient, then there's one other way that we can compensate an anomaly, and that's with a Goldstone boson, okay? That shifts because of an anomalous coupling, a Wess-Zumino term. And that would mean that there's a spontaneous breaking of these global symmetries. Okay, so what are the fermions in the case of QCD at low energies? What are the bound states of confinement that are fermions? Say? The baryons, right? Baryons, in QCD, baryons are fermions. And so you could ask, okay, great. If I take the baryons and I have a hypothesis about how they're formed out of quarks, I can figure out what their charges are with respect to the symmetry. And now I can ask, what is their contribution to these anomaly coefficients? Do they match the anomaly coefficient? And in the case of QCD, the answer is no. The fermions at low energies don't match the anomaly of the fermions at high energies. So that tells you that something else has to enter, a Goldstone boson, to match the anomaly. And that means this symmetry is spontaneously broken. So this is a beautiful way in the 1970s, right, of giving credence to this hypothesis that when QCD confines, it spontaneously breaks the symmetry down to the diagonal because you had to have a Goldstone to match the anomalies. Okay, so Hooft anomaly matching, even in this original form, no higher form symmetries, an incredibly beautiful and powerful idea. And even if you don't like any of the higher form discussion that we're going to have the rest of the lecture today, hopefully you take that away as an interesting application of these anomalies. All right, but our job is not, we care about how anomaly structure now leads to connections between ordinary symmetries and higher form symmetries. So now let's take this idea of Hooft anomalies one step further. And so unlike Hooft, bless you, who is interested in this kind of anomaly diagram, we're going to be interested now in this type of anomaly diagram where there's one insertion of a gauge current and there's two insertions of flavor currents. And the reason we're going to care particularly about those, that will have a very beautiful structure and have interesting dynamical consequences. And also it's something that is present in the standard model. Okay. So crucially, just look at the left-hand side of my squiggly line here. We talked about all of those flavor symmetries of the standard model, right? The U3 to the fifth. Here I've stripped off the U1 factors, but the anomaly coefficients are proportional for the U1s to these SU3s. So I can just go down the list of those SU3 symmetries, right? I have one for each type of fermion in the standard model. And now I can compute the Hooft anomaly diagrams with one insertion of a hypercharged gauge current, right? That's this guy. And then two insertions of the flavor current. And so you can compute the anomaly coefficient. And for one generation of fermions, I've written down the answer here on the right, that all of these flavor symmetries of the standard model have Hooft anomalies with one insertion of a hypercharged current. So this is something, we're going to engage in a little bit of an abstract discussion for the next, 15 minutes. But I want you to anchor the fact that this is happening in the standard model. Okay, so this is something that matters for us. Okay. All right. So the thing that happens when I have one of these Hooft anomalies that involves both a zero form symmetry that we're inserting, those symmetry currents at two of the vertices, and then we have a gauge field. And we know in particular, just to really help orient ourselves, in the case of hypercharge, we know there's a one form symmetry that's valid at all scales, which is the magnetic one form symmetry. Right? So the punchline is going to be that in the presence of these Hooft anomalies, there is now effectively a mixing between the zero form symmetry that participates in the diagram and the magnetic one form symmetry. All right. So this is an example of a very general phenomena, which is known as a higher group. Right, so higher form, those were the symmetries with p-dimensional charged objects and p plus one-dimensional conserved currents. Higher group are now these situations where I have higher form or symmetries of varying degrees from zero form all the way up. And in the presence of Hooft anomalies, they mix. Okay. The nomenclature, again, I didn't make this up. I think it's originally due to mathematicians, and then mathematical physicists adopted it. In general, you can have, a theory that has a p-form symmetry, and maybe it has a p-1 form symmetry, all the way down to a zero form symmetry. So there's some highest degree higher form symmetry in the theory. And if they now mix with each other through these anomalies, we call that structure a p+1 group. Okay, so why the +1, I don't know. All right. The case that we're going to be interested in, just to get our heads wrapped around the idea, is just we're going to imagine we have a zero form symmetry and a one form symmetry. And so what group would that be? A two group. Okay, so we're going to be interested in just a one form symmetry and a zero form symmetry, and so that's called a two group. All right, to understand what happens in a two group global symmetry, I just want to come up with a simple toy model. And then once we've seen the features, then we can figure out how the consequences generalize to the two groups that we actually encounter in the standard model. All right, so our toy model is going to be the following. We're going to have a genuine ordinary gauge symmetry, so we'll call that U1G. We're also going to have some flavor symmetry, so we'll call that U1F, F for flavor. So this is a zero form global symmetry. And this, we're going to imagine there's no monopoles in the theory. So this will have what type of symmetry, global symmetry attached to it? It will have a magnetic one-form symmetry. And then further, we're going to imagine that there is whatever the fermions are that are charged under the gauge group and the flavor symmetry, they're going to be such that there is a Hooft anomaly that again has one insertion of a gauge current and two insertions of the flavor symmetry current. Okay. So it's a Hooft anomaly, and we'll call the anomaly coefficient again, calligraphic A. So now I want us to go ahead, I'm sorry, yeah, just to make sure I get all my nomenclature right. Of course, this is going to have some global symmetry current. I'll call it J mu. This is going to have a magnetic global symmetry current. And with some malice aforethought, I'm going to call the field strength for the genuine gauge field, I'm going to use lowercase f, okay, because we're also going to turn on some background gauge fields. The background gauge field strengths, I'll use capital letters, but just to remind ourselves, this is a real operator valued gauge field, vector, field tensor. We'll just use lowercase f, okay. All right, so now we're going to do the thing that we did in the first lecture, right? We're going to probe the consequences of this by turning on background gauge fields and coupling them to the nominal symmetry currents of the theory, okay? Now, of course, because we have a Hooft anomaly, that is actually going to activate the anomaly, so we'll get an extra consequence, not just invariance of the theory under the background gauge transformations. But we go ahead and we do exactly what we did before. So we're going to add to the action to couple these background gauge fields, right? So the familiar thing already, we're going to couple a background gauge field A mu to the zero form symmetry current, right? That's the familiar thing we did in our first lecture. And we're also going to couple, now we have to turn on a background gauge field coupled to the magnetic one form symmetry current. What kind of background gauge field is that going to be? Yeah, it has to be a two-form gauge field, which is a perfectly reasonable thing. We normally don't talk about them in 3+1 dimensions because we can dualize them to be scalars, but it's a perfectly well-defined object we can add to the theory. So the background gauge field, let's call it B mu nu. We're going to couple that now to the current of the magnetic one-form symmetry. Okay. All right, now let's imagine doing, so let's just do a background gauge transformation, right? So normally, if these are good global symmetries, we do a background gauge transformation. The action and the path integral and the generating functional should all be invariant. So, let's send a mu to a shift by its transformation parameter in the familiar way. And we're going to send b mu nu. It's going to have its gauge transformation. Now, the gauge transformation parameter for a two-form gauge field is itself a one-form. And so the transformation will have that form. But this is just the one-form version of a gauge transformation parameter. That's how a two-form gauge field transforms. All right. And so now we're going to ask what happens to the theory under this background gauge transformation. But we've activated, by turning on the background gauge fields, right, even though this theory had a Hooft anomaly, which, in the genuine theory doesn't do anything to the current, now that we've turned on the background gauge fields, this activates the Hooft anomaly. And so the divergence of the ordinary zero-form symmetry current, is now something which has the anomaly coefficient A. And now one of the field strengths that appears here is the genuine operator, right, F mu nu, the actual gauge field strength of our gauge boson, our real gauge boson. And the other one is the background gauge field, right, that we've coupled to the zero-form symmetry. Okay? All right. So because we've activated the anomaly, if we do this background gauge transformation, right, the action is no longer invariant because we do the transformation parameters, we get derivatives of the transformation parameters, multiplying currents, we integrate by parts, but now instead of having the currents be divergenceless, we pick up a variation of the action, right? So the variation of the action under these background gauge transformations is non-zero. It's minus the anomaly coefficient over 16 pi squared, integral d4x. It's proportional to the gauge transformation of the thing that we coupled to the zero-form symmetry, right? And then it's FF dual. It's actually, it doesn't matter which one we dualize, so I'm going to put the dual on the, what's that? The small f and the big F, sorry? Because again, we have a genuine gauge field, right? We have a gauge theory, U1 gauge theory, that has an actual gauge boson, and it has a field strength with a real operator valued field strength. So I'm calling that lowercase f. Now I've also turned on background gauge fields. These are not operator valued, they're just sources, right? That I'm using to probe the structure of the theory. This has a field strength, this field strength is capital F mu nu. Okay? And so because the Hooft anomaly we're interested in, it's not the insertion of 3 global currents, it's 1 gauge current and 2 global currents. Then when I've turned on these background gauge fields, the form of the divergence now, it's going to pick up 1 genuine gauge insertion and 1 background field insertion. So that's the form, if this were just a Hooft anomaly with 3 global currents, it would be 2 background gauge fields here. But because it's a Hooft anomaly with a real gauge current and a global current, it's 1 of each. And of course, there's the normal question of like what legs get the gauge bosons, but there's always a local choice of counter terms that can put it in this form. Okay. Does that answer your question? Okay. Okay. By hypothesis, I can always write down a theory where I just have one of these mixed Hooft anomalies and no cubic anomaly of the zero form. Right. So let's just imagine that we're just in this case. Okay. All right. But we have one more trick up our sleeves, okay, which is, so again, this where this came from was the background gauge transformation on the first term that we added to the action when we gauged the zero form symmetry. But we also have this second term hanging out. And if we recall that this magnetic one-form symmetry current actually is the form of this field strength of the genuine gauge field, right? That's already living in the action. And so if I simply asked, so this is the gauge transformation of the background gauge field coupled to the magnetic one-form symmetry, this is a good symmetry transformation. If I just do this transformation, the theory is invariant, okay? The reason we had a problem is from this background gauge transformation. But we can restore the invariance of our theory under both transformations if we say that, well, if I was foolish enough to do a background gauge transformation coupled to the ordinary symmetry, I would get some variation. But if I also ask that under such a transformation, I also shift the second background gauge field in a correlated way, I could choose that shift to cancel this variation. Okay, so let's do that, right? If we simply ask that when we do the transformation of A mu, the background gauge field coupled to our ordinary symmetry, we also ask that B mu nu, the background gauge field coupled to the magnetic one-form symmetry, it shift to itself plus the anomaly coefficient over 4 pi. The transformation is dictated by the transformation I did to A mu. Okay, that has to appear here. And then it should be proportional to the field strength tensor of the background gauge field that had this anomaly. Okay, so of course, if I ask under this transformation, I also do this transformation, then this transformation coming from the first term here, the first source coupling, gave us an anomalous variation. But now I have this second with a minus sign. If I also then transform B mu nu, it's already multiplying the F tilde, it's already multiplying this in the magnetic one-form symmetry current. And so this transformation, sourced from this term, precisely cancels the anomalous variation. Okay, so there is a completely good symmetry of the theory, which leaves the path integral and the generating functional invariant under both background gauge transformations. One that's just good on its own is just the background gauge transformation of the thing coupled to the one-form symmetry. That's just a good symmetry on its own. The zero-form symmetry is a bad symmetry, right? It's not an okay symmetry on its own. It leads, in this activation sense, to a variation of the action. But it is restored as a symmetry of the theory if we have actually a coupled transformation, that when we do this transformation, we also do a shift in the other source. Okay, so the existence of the one-form symmetry rescues the zero-form symmetry and gives us a symmetry structure. It is not a separate zero-form symmetry and a one-form symmetry. It is a one-form symmetry and then some correlation with the zero-form symmetry. And so that is the sense in which we mean that the symmetries mix, right? We can't do independent transformations with respect to the two background gauge parameters. We can do one independent transformation and then a correlated transformation. And that is the symmetry of the theory in the presence of this Hooft anomaly. Okay, so you're probably saying, so what, right? You're wishing you'd maybe had another cafe before we came in this morning. But this actually, much like Hooft's argument for QCD, where matching of the Hooft anomalies had dramatic implications for our understanding of the infrared theory, or generally the theory as a function of RG scale, the two-group structure here also has interesting implications. Now, in the interest of time, I'm just going to say it at the word level. I'll leave some more justification in my notes, which will be shared later. But basically the picture is the following, right? In this two-group structure, there's a good symmetry, which is the magnetic one-form symmetry, and there's a bad symmetry, which is the zero-form symmetry. The bad symmetry is rescued only in the presence of the good symmetry, right? So that has an interesting implication as a function of scale. Let's imagine for a moment, again, as we said, it's often the case in an EFT that these symmetries are emergent symmetries that happen in the infrared, okay? So let's imagine there's a scale, we'll call it E1, above which there's no one-form symmetry, okay, and below which there is a one-form symmetry. So that's what we mean by the emergent scale of the one-form symmetry. In the case of the magnetic one-form symmetry here, this would be like monopoles, right? Right, because it's a magnetic one-form symmetry. If they're dynamical monopoles, then the symmetry is broken. And then we can ask the same thing for the zero-form symmetry. Let's imagine it's emergent. So there's a scale above which there's no zero-form symmetry, and then there's a scale below which this symmetry emerges. And let's call that scale E naught. Okay? And so the fact that the symmetry of the theory, right, this is not a good symmetry on its own. It requires the existence of the one-form symmetry in order to be a good symmetry. that tells us that this cannot emerge as a symmetry as we go to the infrared before this is emerged as a symmetry. Basically because there would be a pathology for some regime. If imagine this emerged first as we go to the infrared, there'd be some range of energies in which this symmetry wasn't around to make the theory well defined, right? So there would be a pathology in this background gauge sense. So that must mean, as we go to the infrared, these symmetries either show up at the same time or this one shows up first. In other words, as a parametric statement, the emergence scale of the one form symmetry has to be above or at the emergence scale of the zero form symmetry. Now, you're totally forgiven if you don't find this argument persuasive. There are many other ways of justifying it, some of which I'll leave in the lecture notes, and I can point you to other references that buttress this statement more. But the thing that's interesting for us is when we have a two group, there's a good part and a bad part of the symmetry. And the statement now is, if these symmetries emerge in the infrared, the bad part can't become a symmetry at a higher energy than the good part. And that is a non-perturbative constraint on the dynamics of the theory, right? So that's a very powerful thing. And as particle physicists, that's a very interesting thing. Anytime we have a non-perturbative constraint, if we're living in an EFT where these are our symmetries, but we know they're connected in a two group, and we want to ask what can the UV completions, what UV complete theories could give us this EFT, whatever they are, they have to satisfy this inequality. So for any UV completion you try to write down, it's to be true. And that's kind of a remarkable. So you might be asking, well, how does this play out? What does it actually mean, right? What correlates these scales? What guarantees that this is true? And to see that, I want to now take us back to the standard model, where we've seen that we have this very rich two-group structure, where the good symmetry is the magnetic one-form symmetry associated with hypercharge. The bad symmetry is any of our flavor symmetries, right, when we turned off the Yukawas. They all have these mixed Hooft anomalies with these anomaly coefficients, okay? So, of course, in the standard model, we know the standard model itself, the magnetic one-form symmetry is an exact one-form symmetry. But now let's imagine we're in the standard model and we're looking up to the UV. And we can ask ourselves, well, what are the sorts of UV completions of the standard model I might have where the magnetic one-form symmetry of hypercharge is only an emergent symmetry and it's actually broken at some scale as I go to the UV? What's an example of a UV completion of the standard model in which the magnetic one-form symmetry would not be a symmetry in the UV theory? So what gives us monopoles? Like, of course, I could just drop a monopole into the theory and we'll figure out what happens then later. But is there an extension of the standard model that forces monopoles upon me? Some gut. So grand unification, famously, of course, not all embeddings of the standard model gauge group into other groups give you monopoles, but this is something that can easily be classified with group theory. Most of the grand unifications of the standard model that we care about, we actually know when we break the grand unified group down to the standard model gauge group, we get monopoles. Again, Hooft is living rent-free in our heads in these lectures, so they are Hooft-Polyakov monopoles. They are the topological defects coming from the breaking of the unified symmetry down to the standard model. And just examples of guts that would give us these monopoles, SU5 or SO10, Paddy Salam, which is SU4 cross SU2 cross SU2, or something called trinification, which is SU3 squared, SU3 cubed. These are all things that can be broken down to the standard model gauge group, and at the scale of the breaking, they give us magnetic monopoles. So if the standard model gauge group is unified in the UV in these ways, then the scale of gut breaking is the scale at which magnetic monopoles are generated, is the scale at which the one-form symmetry emerges. So now we can ask ourselves the question, what does this emergence inequality mean if we've UV completed the standard model into a gut that gives us monopoles at the scale of its breaking? Right, the statement is, at the scale of the breaking of the gut, above that scale, these symmetries that have the Hooft anomaly, the ordinary symmetries with the Hooft anomaly, can't be good symmetries of the theory. Okay? So what does that mean? Well, let's now look at the anomaly table. So any one of these symmetries has a Hooft anomaly with hypercharge. So it's a statement that any one of these symmetries on its own can't be a good symmetry of these guts. But you can also notice I could make linear combinations of these symmetries, right? Which is to say I can find diagonal SU3s where the anomaly coefficients cancel. For example, I could take Q, U, and E, right? That would be 1 minus 2 plus 1 is 0. Or I could take L and D, that's plus 1 minus 1, that's 0. Those diagonal combinations of these symmetries would be anomaly free. Does anyone know if I put Q, U, and E together into a irrep of a gut group, what is that irrep? Say SU5? Yeah, the 10, right? So in SU5 grand unification, you can ask how do the standard model fermions organize themselves? And Q, U, and E organize themselves into the 10 of SU5, and L and D organize themselves into the 5 bar, right? So if they live in a unified gut multiplet, the only flavor symmetry is the symmetry that acts on them together, okay? So there's a perfect correspondence. Put differently, the individual symmetries are broken because the gut gauge bosons turn some fermions into other fermions. So individual symmetry transformations of those fermions are broken by the exchange of the gauge bosons. But fermions that transform together in the same multiplet, that combined flavor symmetry is preserved by the gauge bosons. Okay, so there's a one-to-one correspondence between the anomaly-free linear combinations you can make of these symmetries and the ways in which you can unify standard model fermions into irreps of these gut groups. Okay. Okay, so you probably would say, look, that's a fun parlor trick, but we already knew in the 1980s how to enumerate all of the possible unification patterns of standard model fermions. So now I just have some super fancy way of doing it. All right, so you maybe don't find that interesting. But there's something even more interesting actually about the emergence inequality, which is also satisfied here, but is satisfied more generally. You could say, here we said we've embedded the standard model in a gut. That's where we got the monopoles from, right? And then we could see, because we had a hypothesis about the UV symmetry, we could see it was the exchange of the gauge bosons that would violate the individual symmetries. But this logic of emergence, it doesn't specify what the exact UV completion has to be. It says if there's a scale above which the one form symmetry is broken, the zero form symmetry is also broken. So now you could say, okay, Nathaniel, instead of saying we get monopoles from a gut, what if I just dropped a monopole in the theory that had some hypercharged field component at infinity, right? Let me just drop that monopole in the theory at some scale. That's a scale now breaking of the one form symmetry. And you're telling me that this zero form symmetries, anyone who has a Hooft anomaly with hypercharge, these zero form symmetries are broken the moment I drop a dynamical monopole into my theory. What's going on? Right? That has to be true. What's possibly happening? Does anyone have a guess as to what happens? Okay. There's a beautiful phenomenon which doesn't involve Hooft's name called the Kalin-Rubikov effect. It's the statement that fermions, which have chiral symmetries like these, scattering off of monopoles violates those global symmetries. Okay, so Kalin-Rubikov itself would be several lectures, so I'm just going to give you the words and the pictures. But the idea is if I have a monopole in my theory, so this is my monopole, and I scatter a fermion off of it, and that fermion maybe has a global chiral symmetry, that symmetry can actually be forced to be broken in the scattering process. Now, in the olden days, the way that we did this was we basically enforced all of the conservation laws that we knew had to hold, so the conservation laws associated with the gauge symmetries and with the other absolute symmetries of the theory. And once you imposed all of those constraints, in the presence of the boundary that is created by a monopole in the scattering process, you simply could not, something had to give, and you couldn't conserve the global symmetry. And so you learned that these scattering processes had to violate the global symmetry. Okay, so the Kalin-Rubikov effect, there's actually two pieces to it. We're going to focus on the non-controversial piece, which is just that chiral symmetries of fermions are generally broken in scattering off of monopoles. And in the 1980s, if I gave you a collection of fermions with different chiral symmetries, and I gave you a monopole with some field configuration, and I asked you which chiral symmetries are going to be broken, you would sit down and you would do a bunch of tedious calculations and you would find different linear combinations, and some of the symmetries would break and some wouldn't. But in modern language, there's a one-to-one correspondence between the chiral symmetries that have a Hooft anomaly with respect to the gauge group, that the monopole has a field. Though everyone who has a 2 group with that gauge group is broken and scattering off of the monopole. And so that is how this is always satisfied, right? The moment I break the one-form symmetry by putting a monopole in, there is also at all higher scales a process that violates the zero-form symmetry, namely the Kalin-Rubakov effect. Okay. So this is true in these grand unified theories, right? But it's also true just very generally if I drop a monopole into the theory. So what this is reminding us of is the existence of this beautiful non-perturbative phenomenon, and it's giving us a perfect bookkeeping apparatus to understand which symmetries are broken by the Kalin-Rubakov effect, which we did not have, when this phenomenon was first discussed in the early 1980s. And so from a particle physicist perspective, this is incredibly interesting because now we have a beautiful tool for understanding if I have a theory with some flavor symmetries and I have a monopole in the theory, there are dynamical processes that I can now compute easily that tell me about the violation of the global symmetry. All right. Good. I want to give one more example in the last 10 minutes of today's lecture of higher group structure, and then we'll save ABJ anomalies and non-invertible symmetries for the start of last lecture. So this was the standard model. Let's now do a little bit of physics beyond the standard model. Again, if you're doing particle theory in the US these days, you can't swing a cat without hitting someone who works on axions. I don't recommend swinging cats, but if you did, you'd probably hit someone who worked on axions. And it won't surprise you that axion theories also have this rich generalized symmetry structure. So let's just consider a toy model right now, which is a proxy for the axion of QCD. So let's do axion Yang-Mills. So by that I mean, let's just imagine we have an SUN gauge theory. If you wanted to take n is equal to 3, then of course that would be QCD. We're not going to worry about quarks right now. They complicate the story, but not in a fatal way. They just make it a little bit harder to explain what's happening. So let's ignore the quarks for now. And then that's the statement, right, that we have an axion. And to say that it's axion Yang-Mills theory, right, so of course we have the ordinary kinetic term for the SUN gauge theory, the ordinary kinetic term for the axion. But now we imagine, like they are in the QCD axion, that these two are coupled. The Yang-Mills theory can have a theta parameter, but it couples in exactly the same way as the axion to GG dual. All right. So now we can ask, what are the global symmetries of this theory? Let's ignore this coupling for now. So let's pretend we'd set this to 0. We were just looking separately at the pure Yang-Mills theory, SUN, and the pure axion theory. There are 3 global symmetries of interest. Does anyone want to tell me what one of them is? There's a Peccei-Quinn symmetry. So there's the axion shift symmetry, right? The idea is the axion is a Goldstone boson of a spontaneously broken anomalous symmetry. That's why it shows up here. And so that is a shift symmetry. Morally speaking, it has an ordinary zero-form symmetry current, which is just a space-time derivative of the axion. This is the normal shift symmetry of the axion. So this is a zero form. Although for people who do axion theory, this is the symmetry that they care about. We do not care about this symmetry. Okay, don't care. Not interested. There's 2 other symmetries that we are interested in. Does anyone want to hazard a guess as to a second symmetry? Again, let's ignore this coupling. And now we know about higher form symmetries. We know I have a periodic scalar, and we know I have a pure Yang-Mills theory. So we have 2 more symmetries, which are higher form global symmetries. Sorry? The center? Good. Yeah, so as we said, right, pure SUN has a Zn center symmetry, and we now know that's a one-form symmetry. So there's not a continuous current, right? So I'm not going to try to write down a current, but there's the Zn center that we now know is a one-form symmetry. Okay, there's one more higher form symmetry. Does anyone remember this lecture? Yeah. There's a two-form axion symmetry, the winding symmetry, right, which has a 3-index antisymmetric tensor current that we made from Levi-Civita. And so this is a two-form. Okay. So those are our three global symmetries in the theory without having turned on this coupling. Now, it turns out there's a higher group structure here. To show you that there's a higher group requires us to develop even more technology that has to do with Hooft anomalies that involve continuous and discrete symmetries. There's a lot of work required to do that, so I hope you'll just indulge me and take it on faith that actually it turns out there's a Hooft anomaly between the center symmetry and time reversal symmetry, and the consequence of that anomaly is actually now the one-form symmetry and the two-form symmetry mix, and so they form what's called a three-group. Right, so the highest degree was a two-form, so we add one to that for whatever reason, and that's our symmetry. And just as in the two-group symmetry we discussed, the highest form symmetry now is the good symmetry, and the lower degree symmetry, which has the anomaly, is the bad symmetry. But again, there's a three-group. As long as the two-form symmetry is present, it cleans up the anomalous variation of the one-form. So they form a three-group. So now we can say, okay, we have this incredibly strong statement that anytime I have a higher group structure, if the symmetries are emergent in the infrared, the bad symmetry cannot emerge before the good symmetry as I flow to the IR. All right, so that's the statement that the two-form winding symmetry is a good symmetry down to some scale, and the center symmetry cannot be a good symmetry until we get below that scale. Okay. So now you can ask yourself the question, okay, how is this satisfied? And again, it's going to be satisfied in two ways. Let's first think about a perturbative UV completion of the EFT that gives us the EFT at low energies and see how it's satisfied there. And then let's remind ourselves that this had to be true regardless of the UV completion and see that there's a non-perturbative phenomenon which is baked into the story that also guarantees the emergence is satisfied. So the simplest UV completion of axion Yang-Mills is what we would call a sort of a KSVZ axion model. So that's a theory where we have still the SUN gauge symmetry. And we have a continuous zero-form symmetry, global symmetry, the Peccei-Quinn symmetry. And there's some fermions that are charged under the Peccei-Quinn symmetry and SUN that give us an ABJ anomaly. So the Peccei-Quinn symmetry is anomalous. Okay? So we imagine we've got some fermions that are charged under both of these groups. And we also imagine we have some scalar, which is just charged under the Peccei-Quinn global symmetry. And then we can write down in the UV theory, we can write down terms in our action. We can have a Yukawa coupling that involves the scalar and let's say two fermions that are charged under the Peccei-Quinn symmetry. And then of course we can write down a potential for the scalar. And let's imagine the potential is such that it acquires a vacuum expectation value. Okay. So what'll happen, right, is the scalar gets a vacuum expectation value. It spontaneously breaks the UN Peccei-Quinn symmetry. In that case, as we know, it's convenient in the presence of spontaneous symmetry breaking. We're going to have a VEV, which will be F here. We'll have a radial mode. And then we have a phase mode, which we'll call the axion. Okay, that's a convenient parameterization. We spontaneously broken a UN global symmetry. There will be a goldstone, which is the axion. Okay, it has 2 pi periodicity because it's coming from a continuous global symmetry. And now we can ask, we can see that we get an effective theory below the scale of the symmetry breaking, which is just axion Yang-Mills. And the way that we see it is we say, okay, if I want to now integrate out the fermions and integrate out the radial mode of the scalar to just get the effective theory of the light mode plus the gauge group, It's actually really painful if I just plug this in up here to integrate out the fermions, because I have this e to the I axion multiplying the fermion masses. That's a pain. So let's do a complex rephasing of the fermions to move the phase from the mass. Because of the anomaly, it pops out in front of GG dual. So I promised you when I first introduced axions as a solution to strong CP, I said, if we had a field that coupled in the same way as theta, that would relax the theta angle dynamically. And it might look weird to have a field that couples that way, but now we see it's a natural thing. When we've broken the symmetry, this pops up in front of a fermion mass term. We can eliminate it in front of the fermion mass term by rephasing the fermions. But because that rephasing is anomalous with respect to SUN, it means I just shift the coefficient of SUN by the rephasing, which is precisely the axion over its decay constant. So that's how it pops up there. Okay, so we integrate out the massive fermions and the radial mode, and it gives us this axion EFT. Now we can ask about the emergence criteria. Good. So maybe the easiest one to see is actually the scale below which the center symmetry emerges. Does someone want to tell me what's the scale? So in the UV, I claim the center symmetry is not a good symmetry. And in the IR, there is a center symmetry. So what's the scale at which the center symmetry becomes a good symmetry? Remember, the center symmetry is broken by things that are charged under the center. We only have two sets of objects here, right? One is the gauge bosons. Those are in the adjoint. They're not charged under the center. The other one is the fermions. They are charged under the center, as they must be to generate the ABJ anomaly. So this symmetry is broken at the mass scale of the fermions, which is a Yukawa coupling times the scale of spontaneous symmetry breaking. Right? That's the scale below which we've integrated out the fermions. The center symmetry is now a good symmetry. You have to think a little bit more carefully about the emergent scale of the axion symmetry. But it turns out this emergent scale is actually just related to the string tension of the axion strings in this theory. There's lots of ways to argue for that. One of them is just that at energies around the string tension, there are processes like string anti-string formation or string loop formation, which mean that the strings become dynamical. And now, at least locally, I can change the winding number, even if globally I don't. All right, so in some sense, it's the tension of axion strings, which is the scale of spontaneous symmetry breaking. This is the scale below which the winding symmetry emerges. So, okay, in the perturbative regime, which is the regime in which I could write this theory down and calculate, it is, of course, the case that this Yukawa is less than or equal to 1, within a factor of 4 pi. And so, indeed, I satisfy this inequality. Actually, it turns out the inequality is satisfied even more strongly. You could say, what happens if I cranked up the Yukawa coupling, right? Tried to violate this inequality, made it much larger than 1. But if you compute, this is the tree level potential right here. If you compute quantum corrections to the tree level potential, Yukawa couplings have the property, they give a one loop correction proportional to 4 powers of the Yukawa that destabilizes the vacuum. So indeed, if I tried to be clever and made this very large to violate this inequality, I would actually find that I destabilize the vacuum. So the vacuum structure of the theory really enforces this inequality. Okay, so that's cool. It's just an example in a UV completion of how these inequalities have to be satisfied. This was an example, but the statement is, right, if I have this EFT, any UV completion, something has to happen to do this, right? So it's a powerful non-perturbative constraint. Sorry? No, so, okay. This is being recorded, so I'm gonna tell you why lambda doesn't enter here after it's not being recorded. All right. There are divergent statements in the literature about whether lambda appears here or not, and I'm extremely confident it does not. But we can talk about that later. Good. But you could also say, just like in the case of the 2 group, right? Sure, if we had a specific UV completion like a gut, we could see how the inequality had to be satisfied. But we also just knew, even if I just dropped a monopole in the theory, something else had to happen that would satisfy the inequality. And the same thing should be true here. If I didn't have this specific UV completion, if I just drop an axion string that's dynamical into the theory, I should satisfy this inequality. And if it's not, for example, a perturbative model, the string may not actually be an extended object, right? It may not have any sort of structure to it. And so something has to happen to satisfy this inequality on top of what's happening in the perturbative example. And indeed, there's something that happens. It's actually the existence of this phenomenon is easiest to see in this perturbative model. So the axion strings in this UV completion, again, they correspond to, in 2+1 dimensions, vortices, right? Which is just a statement that at infinity, I could have my field pointing in different directions in a way that has a winding number that's well defined, right? And then that means at the core of this, actually, the vacuum expectation value that breaks the symmetry has to go to 0, and the symmetry is restored at the core. And then as I extend this into a string configuration by pulling it out into the extra spatial dimension, that means there's a restoration of the UN-Peccei-Quinn symmetry happening at the core. And although these fermions that break the center symmetry are massive, right, when symmetry is broken, when the symmetry is restored, they become massless, okay? So there's actually what we call, so in the core where the symmetry is restored, the fermions become massless. And this is actually a statement that there are fermionic modes that live on the string that are called the fermionic zero modes, right? So string configurations of this sort actually have fermionic excitations that are these zero modes because the fermions themselves are becoming massless as they go to the string core, okay? And that means all along this string, right, even if asymptotically the fermions are very heavy, if I have one of these strings and it's dynamical, all along the string there are fermions, and the fermions carry charges under the Yang-Mills theory, so they violate the center. So what this inequality is telling you is the existence of fermionic zero modes, right, that have to be there. And that's a statement that anytime the string is dynamical and I have the anomaly that gives me the 3 group, there are zero modes that violate the center symmetry. Now, this was an example where the string configuration was actually a topological defect we could construct. But even if it was like a string theory string that had no finite size, there's still a version of this phenomenon called anomaly inflow, which tells you that even if I can't identify the microscopic degree of freedom, the string must support fermionic zero modes that are charged into the center, and again satisfy the inequality. So in this case, in axion Yang-Mills, the inequality non-perturbatively is a reminder of another beautiful phenomenon of anomaly inflow. So anomaly inflow and the Kalin-Rubikov effect are things that people understood in the 80s. Most particle theorists have forgotten about them, but they're extraordinary things and they have interesting physical consequences. And these emergence inequalities are just reminding us of them. Okay, I apologize for going a little bit over. Oh, well, I mean, in this perturbative example, right, you get the zero modes from all of the fermions that become massless that participate in the anomaly, right? Yeah, yeah, but you are guaranteed you have, no, it's true, but you're guaranteed, sorry, good. It depends on the detailed structure of the anomaly, but you are guaranteed, so if the anomaly gives rise to the 3 group, then you are guaranteed that there is at least one fermion zero mode, which is charged under the center. Okay, so it's in perfect correspondence, as it had to be. Right. All right, so just to zoom out, what have we done? We've, last lecture, we recognized that there's this whole much larger class of global symmetries that we could think about acting on extended objects. This lecture, we're particle physicists. We've asked the question of what happens when these symmetries are broken. We've learned that spontaneous breaking is very interesting because it can allow us to understand the existence of new Goldstone modes. That brings the masslessness of the photon into the Hooft paradigm, right, which was something that we wanted to accomplish, so we've done that. We've seen in the case of explicit breaking, although these symmetries are often broken explicitly in the UV and become emergent in the IR, the effects of UV breaking are somehow gentler or softer than they are in the case of ordinary symmetries. And so when we're interested in getting symmetries of a high quality, that's a very interesting thing for us to think about. And then finally, we've seen that they really start to have direct implications for particle physics phenomenology when there are anomalies present, even anomalies in the ordinary symmetries, because they can now lead to mixing between the higher form symmetries and the zero form symmetries, which has, just like the original Hooft anomaly matching, now has consequences for the theory as a function of scale. And so for us, anytime you have an EFT, you can ask, do I have a higher group structure? And if I do, any UV completion you write down, you should be able to find ingredients that satisfy the inequalities. And that's a really amazing thing. All right, so it's a guide for phenomenology. And in the case of the standard model, because the standard model has these mixings, these two group structures, it's present. And extensions of the standard model that people know and love, that they're also present in interesting ways. Now, there's, of course, as we said, we classified 3 types of anomaly, right, at the beginning of our anomaly discussion. Gauge anomalies, which we're setting aside, Hooft anomalies, which we've now discussed, and ABJ anomalies. And so, of course, the reasonable question you should have is, well, what happens if I have an ABJ anomaly of a zero form symmetry, and those gauge fields also have a higher form structure? So what do I get then? And the answer is something that is analogous to the higher group, but is actually much more exotic and interesting. What happens to those anomalous ABJ anomalous zero form symmetries is they become non-invertible. So they have symmetry defect operators that no longer obey group multiplication, but they instead obey a fusion rule. And so it takes our idea of symmetries outside of group-based symmetries into something much richer. And it allows us to answer the question, what is the fate of ABJ anomalous global symmetries? It also has dynamical consequences like the higher group. So we'll start next lecture, our last lecture tomorrow, by working that out, working out non-invertible symmetries and their consequences. It has an even more interesting implication for the standard model, which I'll tell you tomorrow. And then after that, hopefully we'll finish that about halfway through tomorrow's lecture. And then I have a whole laundry list of interesting non-symmetry selection rules, which we can try to fit into the generalized Hooft paradigm in various ways that I would like to tell you about, just to leave you with. But I think we've reached a good stopping point for today, so let's go get some coffee. Thanks very much.